So far, we've talked about the valence bond theory or hybridization theory for describing why molecules become in tetrahedral, trigonal planar, stuff like that. But we haven't talked about the other one. And the other model is called molecular orbital theory, or MO theory. Now, MO theory is a much more comprehensive theory. It's really, really powerful. It accounts for a lot of things that valence bond theory does not. So, for example, a molecular orbital theory, and by the way, on the right is an example of a molecular orbital theory. Molecular orbital theory will account for things like paramagnetism, which is if there's unpaired electrons in the molecule or not. It will account for things like color. It does a great job talking about bonding. Lots of interesting things. In MO theory, the atomic orbitals, the 1s2, 2s2, etc., they are delocalized into molecular orbitals. So what that means is the atomic orbitals are essentially mixed together and molecular orbitals pop out. In the diagram on the left, the far left, the orange orbitals, that's a 1s2, 2s1 atomic electron configuration for lithium. So the left-hand two orbitals are just a lithium atom. And on the far right, you have another set of lithium atomic orbitals, another 1s2, 2s1. And it's in the middle part here that you make the MO diagram, the molecular orbital diagram. So notice here how in this molecular orbital diagram, the left and the right showed the individual atoms. And then the middle part where this delocalization, the mixing is happening, that's where you make the molecular orbitals. This is going to be the way to interpret these MO diagrams. In a molecular orbital diagram, you can have bonding orbitals, anti-bonding orbitals, and non-bonding orbitals. In this class, we're going to talk mostly about bonding and anti-bonding molecular orbitals, but non-bonding orbitals are possible too, but we won't see a lot of them in this class. MO theory is the bomb. It is so cool, and when it works so well. However, the problem with molecular orbital theory is that it's really, really complicated. Even with today's supercomputers, some of these calculations take incredible amounts of time to have happen. Now, one day in the future, I hope you all will have the TI 2000 calculator or something equivalent to it, where you can just boop, 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 enter in some information, and pop out will come out the molecular orbital diagram for some of these molecules. However, we are not there yet. Even iPhones and stuff and Super Samsungs aren't going to make this happen quite yet, unfortunately. Darn it. So anyway, in the meantime, we can still talk about MO. What we're going to do is we're going to look at very simple examples to figure out how this works. So we're only going to look at diatomics, which means two atom systems. So we'll look at things like H2 and F2, stuff like that, but we won't look at CH4 because that has 5 atoms. We're only going to look at two atom system. And also, we're only going to look at diatomics from the first and second periods only. So we're only going to use atoms up to neon. We will not be looking at, say, chlorine, Cl2, or, bromine, Br2. Those are beyond the first and second periods. So we're only looking at diatomics up to dineon. It does seem kind of limited, but it will give us an idea what's going on. And then in future courses, when you do have the TI 2000 or a powerful computer, you can do more with it and you'll make sense of what you're seeing.
Nitrogen is not magnetic. It is diamagnetic. All the electrons in the molecule are paired. Oxygen, however, interacts with a magnetic field because it is paramagnetic. This physical property indicates that molecular oxygen has unpaired electrons. Molecular orbital theory accounts for this fact, but valence bond theory does not.
So this is kind of a cool little video that shows the utility of MO theory. So first of all, that thing they were pouring the liquids through, that's a magnet, all right? And the magnet is pretty strong, needless to say. But anyway, they put dinitrogen through and no problem, N2. N2 just goes on 2. But oxygen, O2, in a liquid form, which by the way is really unstable. You got to be super careful, keep it super cold. But anyway, they put dioxygen through and you can see it kind of like sticks there between the two magnet heads. And that shows that dioxygen, O2, is paramagnetic. Diamagnetic things just go right on through. They don't care about magnetic fields, but paramagnetic things will stick. And why that's so weird is that if we drew a Lewis structure for O2, and I encourage you to do this, all right? Well, oxygen has 6 valence electrons. There's 2 of them, so that's 12 valence electrons. Divide by 2, 6 pairs. And when you draw this out, O2, draw a bonding pair between the 2 oxygen atoms. You've got 5 more pairs. Outer atoms first, and there's really not an inner atom, so we'll just do that. But you can see that the left oxygen only has 1, 2, 3 pairs. You have to have 4, unless it's boron, beryllium, and gallium, those kind of things, and this is certainly not. So what you do is you take away that lone pair, and you put a bond in right there. So oxygen, diatomic oxygen's Lewis structure looks like this. Each oxygen has 2 lone pairs. There's a sigma and a pi bond for a double bond in the middle. That's fun, but there's no odd electrons. We saw an example in the last chapter of NO2, and it did show literally the odd electron by itself. Oxygen's Lewis structure does not indicate that it's paramagnetic, but molecular orbital, we're going to see, does show correctly that oxygen is paramagnetic. It should stick to the magnet. So if you were just looking at the Lewis structure wouldn't help you here to determine the magnetism. It would give you an incorrect answer. But molecular orbital theory will. And again, MO theory, super cool, very, very complicated sometimes to analyze, but this is going to be one place where we can, even we in our class can see how, MO is really cool. It's the wave of the future. And if you see an ad for the TI-2000 that does MO calculations, please email me right away. I would give you extra credit. Anyway. In molecular orbital theory, there are 4 principles that have to be followed, and we'll go through the principles to kind of lay the groundwork here for what's going on. Principle number 1 is that the number of molecular orbitals must equal the number of atomic orbitals, and there's lots of reasons why, but essentially the number of atomic orbitals you put in equal the number of molecular orbitals you get out. So if you put in 2 1s orbitals from 2 hydrogen atoms, you're going to end up with 2 molecular orbitals in the H2 molecule. If you put 2 1s orbitals and 2 2s orbitals from 2 lithium atoms, then you're going to end up with 4 molecular orbitals in Li2. So remember, like lithium is 1s2 2s1. There's a 1s and a 2s orbital per lithium. So 2 atomic orbitals plus another 2 atomic orbitals from the other lithium makes 4 molecular orbitals at the end. No problem. So let's say that you combine 2 oxygen atoms together. How many total molecular orbitals would you expect? This is the kind of thing you can think about. So oxygen is 1s2, 2s2, 2p4. So each oxygen has 1 1s. It has 1 2s. But if you remember the 2 p's, there's actually 3 of them. You can hold 6 electrons, 2 electrons per orbital, all right? So there's 3 2p orbitals per oxygen. So that means that each oxygen has 1 plus 1 plus 3, or 5 atomic orbitals. So since there are 2 oxygen atoms, that means there's going to be a total of 10 atomic orbitals. Atomic orbitals equals molecular orbitals, should be 10 molecular orbitals. All right. So oxygen has a 1s, a 2s, a 2px, a 2py, and a 2pz. So 5 orbitals total times 2, 10 molecular orbitals in O2.
The bonding molecular orbital has greater electron density in the bond region. The antibonding molecular orbital has reduced electron density in the internuclear region.
When two atomic orbitals make two molecular orbitals, you must always think about, as a scientist, not creating or destroying any energy. First law of thermodynamics still in full force here. So what happens when 1s orbitals come together is one of the new molecular orbitals, there's a lot of electron density between the two atoms. And the lower picture right here, this part I'm highlighting, this is the orbital overlap. You're actually making a bond between the two atomic orbitals. And because the two atomic orbitals are smashing into each other, this is a sigma bond, all right? And in molecular orbital theory, we call this a bonding molecular orbital. So a bonding molecular orbital is just something that makes the molecule more stable. You're saving energy. But if this one is saving energy, you must have something that's using up energy. It's the opposite process. Because remember, you can't have any energy created or destroyed. So the two 1s orbitals will also interact in a way to create an actual node between the orbitals. Now, if you have a node, that's no glue holding the two atoms together. That's going to destabilize the molecule. And we call these kind of molecular orbitals anti-bonding orbitals. Notice the symbolism here. Bonding sigma means that, yeah, you're going to save energy. That's a good kind of orbital, makes the molecule stronger. But there's also anti-bonding sigma star. That little star right there means that it's anti-bonding and it doesn't stabilize. So if you want a molecule to form, you're going to have more bonding molecular orbital electrons than you're going to have anti-bonding molecular orbitals. Bonding makes the molecule stronger, anti-bonding makes the molecule weaker. Principle number 2, the bonding molecular orbital will be lower in energy than the parent orbital, the parent atomic orbital it came from, and the anti-bonding molecular orbital, the one with this little star by it, that's going to be higher in energy than the parent atomic orbital. Once you know what the bonding and anti-bonding orbitals are, you'll start putting electrons in to see what's happening. And you always put electrons to molecular orbitals in the successively higher molecular orbitals. And what this is this is just like we did in atomic orbitals. We always filled in 1s first, and then 2s, and then 2p. Well, in molecular orbitals, we're going to do the lowest molecular orbitals first, followed by the next highest ones and the next highest ones and stuff like that. Now, Pauli exclusion principle and Hund's rule are still going to apply. Electrons in each orbital and stuff, each electron is going to have its own thing. You're not going to have any repeats. All these kind of rules will still apply for molecular orbitals.
In contrast to valence bond theory, which assigns bonding orbitals to individual atoms, molecular orbital theory assigns the orbitals involved in bonding to the entire molecule. The simplest illustration of molecular orbital theory can be seen with the hydrogen molecule. According to molecular orbital theory, the 1s atomic orbitals of the two hydrogen atoms combine to give two molecular orbitals. Because atomic orbitals are wave functions, they can combine either constructively or destructively. Additive or constructive combination of the two atomic orbitals gives a bonding molecular orbital, while subtractive or destructive combination of the two atomic orbitals gives an anti-bonding molecular orbital. The bonding and anti-bonding molecular orbitals formed by the combination of two 1s orbitals are called sigma 1s and sigma star 1s respectively. The bonding molecular orbital, sigma 1s, is lower in energy than the original atomic orbitals. And the anti-bonding molecular orbital, sigma star 1s, is higher in energy than the original atomic orbitals. Like atomic orbitals, molecular orbitals can accommodate a maximum of 2 electrons each, with the electrons in the ground state occupying the lowest possible energy orbitals. The molecular orbitals in the hydrogen molecule can be represented with lines or boxes placed at the appropriate relative energy levels. The 2 electrons in the hydrogen molecule both occupy the bonding molecular orbital. Because most of the sigma 1s bonding molecular orbital is located between the 2 nuclei, Electrons in this orbital draw the two nuclei together by electrostatic attraction. The sigma star 1s antibonding molecular orbital consists of two lobes. The majority of the space occupied by the two lobes does not lie between the two nuclei. In this molecular orbital, the region between the two lobes is known as a node. Electrons in this orbital would actually draw the two nuclei apart by electrostatic forces. Hydrogen has no electrons in this antibonding molecular orbital.
Okay, a lot of information there, but this video is actually pretty helpful, and it's going to actually make you realize why we memorized the 7 diatomics back in Chem 221. And if you remember, it's have no fear of ice clear brew, or whatever version you want to use. Have hydrogen. Hydrogen is one of the ones that naturally exists as a diatomic, H2. And this slide is going to show you finally like what's going on. So in the video, it did a pretty good job, I think, talking about how when the 1s atomic orbitals come together, they make the lower bonding molecular orbital and they make the higher antibonding molecular orbital. And notice the descriptor, it's called it sigma 1s and sigma star 1s. So the sigma is the head-to-head overlap of the orbitals, no problem. The star means, of course, antibonding, but the 1s means that they came from 1s orbitals. And we're going to see eventually here some other orbitals that come from like 2s, so that's kind of helpful too. But anyway, when the 1s orbitals on the hydrogens come together, then they make sigma 1s and sigma star 1s orbitals. So this is the molecular orbital diagram. And initially, there was like a single electron in the left hydrogen and a single electron in the right hydrogen. Then in the molecular orbital diagrams, they both went to the lower bonding molecular orbital. Electrons always go from lowest to highest orbital. One is spin up and one is spin down, all right, to give them opposite spins. But guess what? This is actually the molecular orbital diagram now for H2. And notice how both electrons in the individuals saved energy making H2. This is why H2 is the dominant form of hydrogen. You save energy making the H2 versus the individual hydrogen atoms. And that's kind of a cool thing. So we would describe this then as two 1s electrons from two hydrogen atoms occupying the sigma 1s bonding orbital in H2. And again, the atomic orbitals are just these guys. The bonding molecular orbital is this one right here. The anti-bonding is right there. And because there's more bonding than anti-bonding, H2 is going to happen, which is pretty cool. Now, was helium one of the diatomics, i.e., will there be an He2 molecule? Let's find out. Here's the molecular orbital diagram for the dihelium molecule. Now, helium has one more electron than hydrogen. So while hydrogen was a 1s1, helium is a 1s2. So initially, if you will, you'd have like two up arrows, one up, one down, in each of the heliums. So there's 4 electrons total. And those 4 electrons, the first 2 go in the lower helium bonding orbital, but there's also now some electrons for the anti-bonding sigma star 1s. So there'll end up being 2 1s electrons in the sigma bonding and 2 1s electrons in the sigma star anti-bonding. And the question at this point is, do you think that this is going to form or not? And you can probably guess what it is, but let's formalize it. Bond order is a way to tell if the molecule is going to form or not. And bond order is related to, but not the same as, the bond order we looked at in the last chapter. In the last chapter, we looked at the Lewis structure, so a single bond was bond order 1, a double bond order 2, etc., etc. This bond order is similar, but it's a different definition. When it comes to molecular orbitals, bond order equals 1/2 times the number of bonding electrons minus the number of anti-bonding electrons. If the calculated bond order is greater than 0, that means you have a stable molecule. It's a molecule that can form. On the other hand, if you have a bond order equals to 0, and we're going to see some of those, or in other classes, you actually might have a bond order less than 0, but we won't see them in this class, those molecules are unstable and they probably won't form. So let's apply bond order to the two molecular orbital diagrams we've seen so far. Here's the H2 molecular orbital, and again it shows 2 electrons in the bonding sigma 1s, but no electrons in the sigma star 1s. Hydrogen doesn't have as many electrons as helium. So for this molecule, 1/2 parentheses bonding minus anti-bonding electrons, 1/2 parentheses 2 minus 0, bond order 1. So if the bond order is greater than 0, we'd say it's stable. You bet, hydrogen is a stable molecule. It's something that will exist. Now, it doesn't mean it's not reactive, all that kind of jazz, but it does mean it's something you can put in a jar, if you will, and show your friends. Although hydrogen doesn't really have a color, I digress. It's something that's stable. Hopefully you get the idea. Notice that in this context, the bond order works out pretty well when it comes to the Lewis structure. The Lewis structure for H2 would be like this, all right? 1 electron on each hydrogen making 1 sigma bond. The hydrogen only needs 1 bond, so it's happy. The single bond between the 2 hydrogens would also be bond order of 1, just like the molecular orbital diagram, which again is this part here in the middle, just like the molecular diagram also had a bond order of 1. So often MO and Lewis structure's valence bond will be very similar. Not all the time, but a lot of the time, most of the time, I would argue they will be stable. Let's look at another example. We looked at dihelium earlier. Dihelium has this structure right here, where now both the bonding and the anti-bonding orbitals have 2 electrons inside them. Well, for dihelium bond order, 1/2 parentheses bonding 2 minus anti-bonding 2, 1/2 2 times minus 2 is 0. So dihelium is unstable. Dihelium, to the best of my knowledge, has never been found. There's no energy reason for the dihelium molecule to come together. Each individual helium atom is really stable by itself. There's no reason to form He2. In hydrogen's case, you had a high energy savings making the H2 molecule, so that's why H2 is happening. Bond order was equal to 1. Dihelium, though, each helium is so stable it doesn't need to react, so we would not predict the dihelium molecule to exist. It has a bond order of 0. The fourth principle of molecular orbital theory says that atomic orbitals will combine to give molecular orbitals only when the atomic orbitals are of similar energy. And this is where we'll start to realize why we can only kind of do diatomics with lower atomic number. Similar energy means better overlap. So what that means is that 1s plus 1s is going to be a good molecular orbital combination because the 1s's are very similar in energy. But 1s and 2s won't give a very good molecular orbital. There's quite a bit of energy difference between them. So 2s plus 2s is good, just like 2p plus 2p would be good, but 2s plus 2p wouldn't be very good. 3s plus 2s wouldn't be very good. As you get to bigger atoms, the higher orbitals begin to mix. So like 3d and 4s are pretty close in energy, actually. They'll start to mix together. And the molecular orbital diagrams get very complicated. Not only do you have more molecular orbitals to deal with, but you start having 3d and 4s mixing with another atom's 3d and 4s orbitals. So it can get pretty crazy. And that's why in this class, we're just going to look at things up to dineon, because up to dineon, 1s only interacts with 1s, and 2s only interacts with 2s, and 2p only interacts with 2p. If you wanted to do, say, chlorine with 3p, well, 3p and 3s mixes a little bit, and 3p and 4s mixes a little bit. The orbital mixing gets a little bit more complicated. So again, this is where the TI 2000 one day will take care of this, but in the meantime, we're stuck with simpler examples. So what combination of atomic orbitals would you expect to create the best molecular orbitals? All right. And again, you want to try and pick the ones which are closest to each other as possible. So 1s and 2p? No, I don't think so. 2p and 3p? Probably not. But 3d and 3d, i.e. 2 that are the same, that's going to be a pretty good combination. Now, it's not that 3d won't mix with 4s or something like that, but the best mixing will be when they're like orbitals, 3d and 3d, just like 1s and 1s, etc. Pretty cool. The last one there, E, 5G. Chemists are close to getting to a 5G atomic orbital. We're right now on the periodic table up to about 118. One day, if we get to 121 protons, that would be an atomic orbital that involves some 5G. So I throw in 5G jokes once in a while, even though we're not really there. Cheesy instructor tricks. So let's build the dilithium molecule. Now, dilithium is kind of special to me because, as I've talked about more than once, I'm afraid, I really like Star Trek. And dilithium was the substance that supposedly allowed the warp drive of Star Trek to work, so they could go different places in no time at all. Dilithium in the real world is a compound that can be made, but so far it has no applications to warp drive theory. Darn it! But anyway, I digress. Dilithium is actually a molecule that can happen. So let's look at this picture here on the left of dilithium itself. The far left is a lithium atom, 1s2, 2s1. The far right is a lithium atom, another 1s2, 2s1. And in the middle right here is the mixing of the molecular orbitals. Now the bottom part is the sigma 1s and sigma star 1s that we saw for hydrogen, no problem. But the top part now is essentially a copycat of that one, where we have a sigma 2s bonding underneath and a sigma star 2s anti-bonding on top. Now, the 1s interactions for dilithium, you have just as many bonding as you have anti-bonding. So the 1s interactions, there's no bonding going along. Those are essentially like lone pairs on the lithium. They're not interacting with the dilithium molecule. But the quote-unquote exciting part happens in the top. You've got two bonding electrons in sigma 1s and no anti-bonding electrons in the sigma star 1s. Notice you've got more bonding than anti-bonding electrons. That means you should have a good molecule. But let's compare it. Let's figure out the bond order. 1/2 parentheses bonding minus anti-bonding. So there's 2 bonding here, and there's 2 bonding right there. So that's the 4 bonding electrons. And then right there are the 2 anti-bonding electrons. This one up here is empty. So 1/2 parentheses 4 minus 2, 1 bond order. It's going to be stable. Now, you could have also figured out bond order by just looking at the top orbital interaction. So let's only look at this part right here, and you'd have 1/2 of 2 bonding electrons in the sigma 2s and no anti-bonding in the sigma star 2s. That would also get you to 1. So if you wish to look at bond order only using the top electrons, i.e. the valence electrons in this case, that's totally fine. It's up to you. You can either do the whole molecule or just the top ones. Your call. Lazy chemists a lot of times will look at just the top ones, but honestly, there's nothing wrong looking at the whole molecule. Would you expect diberyllium to exist? Now, beryllium has one more electron than lithium. So beryllium would be a 1s2, 2s2. And if you're going to have diberyllium, you'd have 2s2 on the left and 2s2 on the right. And those extra 2 electrons would end up in the sigma star 2s orbital. So diberyllium we would not expect to exist. It would be 1/2 parentheses 4 minus 4 or 1/2 parentheses 2 minus 2, depending on which orbitals you looked at. It's going to have a bond order of 0. If you have just as many bonding as anti-bonding electrons, there's not going to be any stabilization in the molecule, and it shouldn't happen. The next atoms that could make molecular orbitals involve p orbitals. So, for example, boron is after beryllium. Boron is 1s2, 2s2, 2p1. And when it comes to the p orbital interaction, it's really cool. So you have 3 2p orbitals from the first atom and 3 2p orbitals from the second atom. You're going to end up with 6 total molecular orbitals, and it's kind of cool. So we're going to see some cool kind of pictures here. The 2p orbitals, first of all, will create 2 sigma molecular orbitals, and the other p orbitals will create pi molecular bonds. So we're going to have sigma bonds and pi bonds when it comes to the 2p interaction. It's kind of cool. And of the 4 pi bonds, 2 of them will be bonding, 2 of them will be anti-bonding. We'll call them pi and pi star. Just like the 2 sigmas, one would be a sigma bonding and one would be an anti-bonding sigma. But there's a little bit of a catch when it comes to the 2 p's. There's 2 different orbital diagrams we're going to be looking at. The first diagram we're going to look at is if you have a boron, carbon, or a nitrogen. And sometimes I think about this as the NBC diagrams. NBC, of course, analogous to the TV network NBC. But anyway, that's just what works for me. If you have a BCN or NBC, notice the picture down here showing the 2p interactions. The 1s's would be down here. They're filled and boring, so not that exciting. And the 2s's, you can see right above it, bonding and anti-bonding are both filled, also not very exciting. The BCN orbitals, the pi's are lowest, followed by the sigma, then the pi star, and then the sigma star. So the pi's get filled in first, and then the sigma, then the pi star, sigma star. I'm going to refer to this sometimes as a 2-1-2-1 diagram because the 2 pi's are filled in first, followed by the 1 sigma, then the 2 pi star, then the 1 sigma star. So for diboron B2, boron is 1s2, 2s2, 2p1. So that means there would be a single electron on the atomic side for both borons. And when they come together, they both go to the pi 2p shell, so you'd have 1 electron in each side. Bond order, 1/2 parentheses, bonding minus antibonding. If you look at just the top part, that would be 1/2 parentheses, 2 minus 0, because there's only 2 pi electrons. All the other orbitals are filled bond order of 1. So if you have B2, like this one, or N2, or C2, something with B, C, and N in it, then you're going to use this 2-1-2-1 diagram. There's a handout about this and stuff in the companion. You can look it up and stuff and see. However, remember that in the 2p set there on the periodic table, B, C, and N are just the first 3. The other 3 elements are oxygen, fluorine, and neon. So if you have O, F, and Ne, which I will sometimes abbreviate as phone, which is very cheesy, but F-O-N-E kind of sounds like phone, and of course we all have phones these days, blah, blah, blah. Anyway, this creates what I'm going to also refer to as the 1-2-2-1 diagram. So if you look at this part here to the left of the line I've drawn, the sigma 2p is now lower than the 2 pi 2p's. In the last picture, the pi's were lower than the sigma, so it was the 2 pi's followed by the 1 sigma, then the 2 pi star, and the 1 sigma star. That's why it was the 2-1-2-1. This one is a 1-2-2-1. The sigma is first, the 1 sigma, followed by the 2 pi's, then the 2 pi stars, then the 1 sigma star. So these types of interactions, which are for O2 and F2 and Ne2, which is possible. You want to use the 1-2-2-1 configuration instead of the 2-1-2-1. The bonding orbitals are trading places, but the anti-bonding orbitals stay in the same spots. It's only the bonding ones that kind of make a difference here. This is a picture of dioxygen, O2, and notice how sigma 2p is the first, then pi 2p, then pi star 2p, then sigma star. That's the 1-2-2-1 again for this one. So on this diagram, oxygen is a 2p4. The whole oxygen, remember, was 1s2, 2s2, 2p4. So that means that on each atomic side, you would have 1, 2, 3, and 4. And I'll do it for the other one too. 1, 2, 3, and 4. So you have 8 electrons to put in the middle. The first 2 electrons go to the sigma 2p. The next 2 would go individually to the pi 2p. The next 2 would pair up the pi 2p. And the last 2 electrons, each in their own box, pi star 2p. So bond order here, 1/2 parentheses. And if you're looking at just the 2p, 6 minus 2, that's the bond order of 2. This is going to be a molecule that exists. And since you've been breathing oxygen while you're watching this video, that's probably a good thing. Woohoo! Yeah, go oxygen. Oxygen is absolutely stable, which is cool. Punchline here is that when you get to the boron through neon diatomics, you've got to realize that there's a change that happens between the NBC and the FONEs. And the difference is this is the bonding orbitals, all right? It's a 2-1-2-1 when you get the NBCs, and on these guys, the OFNEs, it's a 1-2-2-1, sigma first, then pi, etc., etc. Magnetism can absolutely be described through molecular orbital theory. And if you remember from atomic orbital theory, if you had 1s2, 2s1, the 2s1 had a single box with an odd electron, so that was paramagnetic. Well, in a molecular orbital diagram, you just look and see, do you have any unpaired electrons? And you absolutely do. In O2, 2 individual electrons right there. O2 is absolutely paramagnetic. You've got unpaired electrons. They're in pi star anti-bonding orbitals, but that's it. Now remember, this is cool because O2's molecular orbital diagram shows that O2 is paramagnetic. If you're to draw the Lewis structure for O2 looks like that. There's no odd electrons running around on that thing. So MO is much cooler for oxygen's diagram than the Lewis structure is, which is kind of a neat thing. Dinitrogen is an NBC diagram. It's a 2-1-2-1. So you can see that here now the pi's are lower than the sigmas, but the pi star and the sigma star are the same. That's where the 2-1-2-1 comes from. Now, nitrogen, the atom, is 1s2, 2s2, 2p3. The 2p3 means we would draw 3 electrons on the left, 3 electrons on the right, and they'll combine 6 electrons in the middle, so the pi 2p is filled as well as the sigma 2p. But notice that every up electron has a down electron. There are no unpaired electrons, so N2 is diamagnetic. The Lewis structure for N2 is very, very close to the molecular orbital theory structure. N2's Lewis structure would look like that. It has a triple bond order of 3, just like molecular orbital diagram shows bond order of 3. N2's Lewis structure shows it to be diamagnetic, and so does the molecular orbital diagram. N2 would go right on through the magnet with no problem. Is N2 plus paramagnetic or diamagnetic? This is a cool kind of part about molecular orbital theory as well. It's easy to find if the ions of neutral atoms are paramagnetic or diamagnetic. Now, N2 plus means you've lost 1 electron. So if you look at N2, the diagram there on the right, N2 plus means that it's going to lose one of the electrons, and it's always the highest occupied molecular orbital electrons that come out first. So for N2 plus, we would take away one of those bonding sigma electrons. Then there would be just one electron left over. N2 plus is going to be paramagnetic. N2 minus, one extra electron, would also be paramagnetic because we'd have to add that extra electron to the lowest unoccupied molecular orbital, the pi star 2p. Pretty cool. It's easy to tell with molecular orbital diagrams, a lot of information on the ions of molecules if you have the default molecular orbital diagram listed. We'll look at that more in the problem set as well. Instead of drawing out the complicated 1-2-2-1s and 2-1-2-1 kind of diagrams, you can use a shorthand notation to represent your molecular orbital diagrams. These are really handy. They're a lot easier to draw in Microsoft Word or Google Docs than the full diagrams with pictures and stuff like that. Molecular orbital notation, a lot of times what they'll have a core or core electrons, and that shows the orbitals which basically aren't interacting. If you have just as many bonding as anti-bonding orbitals, then you could just write core for those. Also with molecular orbital notation, you always want to go in increasing energy. So lowest energy on the left and highest energy on the right. That would be like going from the bottom to the top on the other diagrams. This is the molecular orbital diagram for N2 on the left, and it's pretty cool looking. In terms of a molecular orbital shorthand notation, all right, this down here would be how you'd write it. In this case, core, or core electrons in brackets, that's equivalent to the noble gas notation. So like lithium is a helium in brackets 2s1. Core, or core electrons in brackets, means that there's sigma 1s and sigma star 1s electrons, which are filled up. So for this shorthand notation, you would write core, and then notice the notation. Sigma 2s is in parentheses with a superscript 2. So this is the molecular orbital, the sigma 2s, parentheses, and then superscript represents the number of electrons. So sigma 2s2, sigma star 2s would be the next one, 2, pi 2p4. You can combine them both. You don't have to separate them. Pi 2p with 4 electrons, sigma 2p2. Once you get used to the notation, it is a lot easier to write than the diagrams on the left. I want you to draw, at least at first, some diagrams like the one on the left because it kind of shows where all this stuff comes together. But when you're used to it, the shorthand notation is definitely the way to go. So the question is, what's the bond order of N2 plus? All right, and there's 5 different possibilities there. Now, in the lower corner there, it shows the shorthand notation for the N2 molecule. And it said core, and then sigma 2s2, sigma star 2s2, etc., etc. When you're figuring out bond order, remember if the bonding and the anti-bonding are equal, they really don't participate in the bond order. So we can absolutely ignore the sigma 2s2 and the sigma star 2s2 electrons. They're not really part of the bonding. And we also saw earlier that N2 has a bond order of 3. That came from 1/2 parentheses, bonding minus anti-bonding parentheses, or 1/2 6 minus 0. And the 6 comes from the 4 of the pi 2p and the 2 of the sigma 2p. So 1/2 parentheses 6 minus 0 is where the bond order of 3 came from for neutral N2. Now N2 plus, we've taken away one of the bonding electrons. We're going to take away the sigma 2p, and so it'll only have sigma 2p1 after that. So bond order of N2 plus would be 1/2 parentheses 5 minus 0. We don't have 6 because we took away one of the sigma 2p's. 1/2 parentheses 5 minus 0, bond order 2.5, 2.5. Now you can easily represent partial bonds, like half bonds in molecular orbital theory. In a Lewis structure, it's difficult to try and draw half bonds. Like we talked about how when an item resonates, sometimes you can have like fractional bonds. In molecular orbital theory, it's easy to talk about 2.5 bonds or 1.5 bonds because it's all about the raw electrons, all right? This is another advantage of MO theory. It's a lot better at talking about these partial bonds than any of the other systems we've looked at so far. You can also determine the number of sigma and pi bonds in a molecule using molecular orbital theory. When you're talking about sigma and pi bonds, you must focus on the sigma orbitals versus the pi orbitals, and you don't mix them together, all right? And then also along the way, just like we saw in chapter 7, number of sigma bonds plus number of pi bonds equals the bond order. So let's go back to N2 real fast. The Lewis structure for N2 looks like this. It's a triple bond, which means bond order of 3. And as we saw already now, the first line you draw is a sigma, so there would be 1 sigma, and the other lines you draw would be pi. So the triple bond order of 3, has 1 sigma plus 2 pi. And that's what we're going to do in the equivalent version here with molecular orbital diagrams. To figure out the number of sigma bonds, we're only going to look at the sigma orbitals. To figure out the pi bonds, we're only going to look at the pi bonds, pi orbitals. And finally, sigma plus pi will equal the overall bond order, which is a nice way to check yourself. So for N2, all right, here's the shorthand notation. Sigma 2s2, sigma star 2s2, pi 2p4, sigma 2p2. Notice here that in this picture, all of the sigma electrons are that kind of green color, and the pi electrons are the kind of orange color. So you can see there's 4 bonding pi's, and there's a total of 6 sigma electrons, but 2 of the sigma electrons are anti-bonding and the other ones are bonding. So if you want to figure out number of sigma bonds, 1/2 parentheses bonding minus anti-bonding, but just the sigma, all right? And in this molecule, these are bonding sigmas, these are bonding sigmas, so there's 4 bonding sigmas. We'll subtract the 2 anti-bonding sigmas, 1/2 4 minus 2, 1 sigma bond. We're going to do the same kind of thing for pi bonds. 1/2 parentheses bonding pi minus anti-bonding pi. There are no anti-bonding pi's. Those would be the ones up there, and those are empty for this diagram. So 1/2 parentheses 4 minus 0, bonding minus anti-bonding, 2 pi bonds. And the overall bond order, 1/2 parentheses bonding minus anti-bonding, well, this is the anti-bonding, and all the other ones here are the bonding. So 1/2 parentheses 8 minus 2 is 3. That would be the bond order, and that's good because that also equals the number of sigma plus the number of pi's. So a bunch of things here. First of all, bond order still equals 1/2 parentheses bonding minus anti-bonding. That'll give you a number. And sigma bonds, 1/2 bonding sigma minus anti-bonding sigma will give you the sigma bonds. Pi bonds, 1/2 bonding pi minus anti-bonding pi will give you the pi bonds. And if you've done it right, sigma plus pi will equal the overall bond order. That's a nice way to check yourself, all right? Finally, the N2 molecular orbital diagram is really, really close to the Lewis structure N2, which I kind of cheesy wrote up there. You're still going to have a bond order of 3, 1 sigma, and 1 pi, all right? If you're curious about where the lone pairs come from, the lone pairs come from these electrons right there. One of them is on the left nitrogen, one of them's on the right. Again, there's no molecular orbital diagram, so those electrons are being separate on each individual nitrogen. Oh, it's all coming together and everything's diamagnetic. So N2 is a good success story for MO versus Lewis structure / valence bond theory. This picture here shows the MO diagrams for the neutral diatomics between B2 and Ne2. And there's a left and the right. On the left-hand side, we're seeing the 2 1, 2, 1 diagrams, where the pi's are first and then the sigma, then pi star and sigma star. On the right side, we're seeing the 1, 2, 2, 1 diagrams, where the sigma now is first before the pi, then pi star and sigma star. And you can see how the things change. Bond order gets up to a high of 3 and then goes down to 0. Notice there the energy, bond enthalpy. That's essentially a measure of the energy. Remember in the last chapter we saw as bond order goes up, the bond energy goes up. We definitely see that bond order 3 has the most energy relative to 2s and 1s. Notice the 2 from C2 is different than the 2 from O2. That's because of the different electronic configurations. We also saw that as bond order goes up, the bond length goes down in a relative context. So you can see that as bond order is going up, the bond lengths they're represented in angstroms, that A with the circle on the top. Bond lengths are going down to nitrogen, and then they start going up and you go to the other side. And finally, you can also see the magnetism, all right? B2 and O2, of course, each have unpaired electrons there, so they're going to be paramagnetic while the others are generally diamagnetic. The reason they try and rationalize why there's the 2-1-2-1 versus 1-2-2-1 diagrams is because of the sp mixing and or electron repulsion. I don't really buy either one of them, so I think this is an area where scientists still have to figure some stuff out. But anyway, if you're curious why there's the NBC versus phone or the 2-1-2-1 versus 1-2-2-1, those are the reasons they give. I'm not totally in love with either one of them, though. Making the ions is actually pretty simple. We did some cheesy examples earlier. Let's formalize it right now. If you're making a cation, a positive charged version of your molecule, you're going to take an electron away from what's called the highest occupied molecular orbital. So O2 neutral had pi star 2p2, that there was 2 electrons in pi star 2p. But this diagram is for O2 plus 1. So they took an electron away from an anti-bonding pi star 2p. Once you make the new ion, which by the way you can see is easy, you just add or subtract electrons, you need to recheck your bond orders, paramagnetism, diamagnetism. Another thing is that since we took away a pi star, an anti-bonding electron, we would expect the bond order to go up because we're taking away an anti-bonding electron. If you took away a bonding electron, we would expect the bond order to go down. We're destabilizing the molecule. But it's pretty easy, which again is an advantage for having an MO diagram. If you wanted to make O2 minus, you'd start with neutral O2, and the picture right there is of neutral O2. It's got the pi star 2p. And the question is here, where would you place the extra electron? Well, the extra electron will go in what's called the lowest unoccupied molecular orbital, the LUMO. The LUMO here would be a pi star 2p. That's the first place. You could pair up one of the electrons, either left or right, it doesn't matter. We are adding, though, an electron which is going in an anti-bonding orbital. So we would not expect the O2 minus 1 ion to be as stable. Adding anti-bonding electrons makes the molecule less stable. If you add bonding electrons, or if you take away anti-bonding electrons, you'll make the molecule more stable. So it's kind of cool how everything works out.
When light strikes an object, part of the light is reflected. In the eye, electrons in rhodopsin move from a pi bonding orbital to a pi anti-bonding orbital. One of the molecule's double bonds turns into a single bond, allowing rotation. The double bond then reforms, and the molecule locks into a new shape. The change in shape triggers a nerve impulse, and we perceive light.
This is a really cool use of molecular orbital theory, and it helps us to understand the process of seeing red. When your eye sees red, the light comes in, and it's the perfect, apparently, wavelength and energy to make one of the pi bonds in rhodopsin, this chemical, break apart. And what that means is the pi orbital, which initially has 2 electrons, one of the electrons gets enough energy to jump up to an anti-bonding pi orbital. And if you have just as many bonding pi as anti-bonding pi, it breaks that double bond. And by breaking the double bond, the molecule rotates into this meta-rhodopsin, which is kind of a cool name. And that transition allows a nerve impulse to go in our brains and say, hey, that's the color red. Pretty cool. After a while, the meta-rhodopsin relaxes back to rhodopsin, so it can absorb more light. You see more red and stuff like that. But anyway, this is a cool kind of thing. Rhodopsin is a really interesting compound. If this is something you're interested in, this would make a great class presentation molecule or compound. Rhodopsin, and the chemistry behind seeing is really neat. This is all photochemistry, using light to enact chemical change. Pretty cool stuff.
As a lithium crystal forms, the electrons and orbitals of individual atoms interact to form molecular orbitals. As more and more atoms join the crystal, the orbitals become so numerous that there are too many to account for with standard box notation. Instead, we describe a band of molecular orbitals which is spread or delocalized over all the atoms of the metal.
The third type of bonding is called metallic bonding, and we've seen a lot of examples with ionic bonding, positives and negatives. We've seen a lot of bonding examples with covalent bonding, which is nonmetals and nonmetals. But in metallic bonding, you have pure metals or combinations of metals, and when they mix, instead of having like one lithium atom, you'll have a whole bunch of lithium atoms, and they're all at the same energy. So those energies essentially mix together, and you end up with a whole bunch of occupied bonding molecular orbitals and a whole bunch of unoccupied, usually anti-bonding molecular orbitals. And if you add a 10 to the 23rd of these, they create what's called band theory, which is basically a separation between the bonding and the anti-bonding orbitals. This creates essentially what they call a sea of electrons, which flows over the metal. And these sea of electrons are why like metals conduct electricity so well. Electron goes in one side and out the other because it's just a big sea of electrons. Very, very cool stuff. This is only possible, of course, if the molecular orbital energies are very close to each other. So alloys are generally metals that are similar molecular orbital wise to each other, but you do get excellent overlap. Metals will kind of bend a lot of times because the sea of electrons just flows with it. However, it's usually harder than to boil metals, because in boiling you break the band apart and stuff, makes it really tough. So band theory is pretty cool, and this also gives us a chance to talk about metallic bonding a little bit. This actually shows 2 rhenium atoms that are bonding. This is a true metallic bond in carbon nanotubes. And there's kind of like 2 tubes, like one above and below, and like a little channel in between. And the dark little spots there, which were interacting, those are 2 rhenium atoms. And they were actually able to observe this. This is January 2020. So it's pretty cool. You can actually see this kind of stuff in the real world. And anytime I can show my chemistry home movies, I will try, because it's just so freaking awesome. Anyway, that's it for Chapter 8. So we looked again in this section at valence bond theory and molecular orbital theory, and hopefully you've got a better idea like what's going on. Definitely on this stuff, I recommend looking at some of the things to help you along. There's a study guide with bulleted highlights of the concepts from this section, and I definitely recommend you look at that. The concept guide has some worked problems from the section, so if you're not curious, if you're kind of uncertain how molecular orbital theory works, I encourage you to check that out. Following this slide, if you're looking at the lecture notes, there are some important equations to help you get through this stuff, and also some end of chapter problems. So the questions are on one page and the answers are on the next. Try and do the problems yourself, check yourself, see if they're good. Should be good to go. Feel free to reach out if you have any questions on this stuff. I know this can be weird. You can reach out to me via email. You can also talk to the Learning Success Center / Avid Center above the library. Any of these ways are great. I encourage you to do so. Okay, good luck with your studying and have a wonderful day.